Hello everyone. In the previous lecture, we have done some numericals based on electric field. In this lecture, we will continue with further discussion on the topics in electric charge and field. The first topic here is called as electric lines of force. We have seen in the previous lectures that if we have a positive charge or even a negative charge, we know that each charge creates an influence around itself. Now, because of this influence, one more charge placed in that field experiences a force. This influence was called as electric field. Electric field is seen through electric force, but electric fields are physical quantities. We can't see them physically, so we can't even draw them also. So to represent this physical quantity, we need a method, or we need some kind of a arrangement, and that representation is called as electric lines of force. To define it, we can say a line of force in an electric field is an imaginary line along which a unit positive charge tends to move when placed in that field. So if you have a charge as given here, these are lines which are imaginary. These lines could be straight or they could be curved also based on the charge configuration. An example is given here. So a line drawn like this, these are called as electric lines of force, and these are imaginary lines. Now we will see what these are in a minute. Before that, we will look at some characteristics or properties of lines of force. The first property or characteristic is that electric lines of force are radially outward for an isolated positive charge and are radially inward for an isolated negative charge. As seen here, if we look at a charge which is isolated, now here it means that there is a single charge which is not interacting with any other charge at all. So think of a configuration or think of a condition where we have a charge very far away in the universe or in the space. Think of a charge very far away. So if this charge doesn't interact with any other charge, then we can assume that this is an isolated charge. So for such configuration, if it is a positive charge, then the lines of force are radially outward as given here, and if it is a negative charge, then the lines of force would be radially inward as given in this configuration. That's the first point. Second point is electric lines of force originates from a positive charge and terminates at a negative charge. That is, if you have configuration of two charges, so assume that we have charge somewhere here and then somewhere here we have one more charge. So in this case, the lines of force would start at the positive charge and these lines of force would end at the negative charge. We will see as to how to get this in a minute. For now, just assume that if we have a positive charge and a negative charge, then the fields of line would start from the positive charge and end at the negative charge. Look at this line of force for a minute. It starts from here and goes and goes to the negative charge. Even this also starts from positive charge and goes to the negative charge. The third point is the direction of tangent at any point on a line of force gives the direction of electric field at that point. Suppose in this configuration, if I wanted to find the electric field at a given point here, at this point I need to find the electric field. Then we can draw tangent at this point. Now in this case, since the field lines are going like this tangent will have direction like this. It will be something of this kind. So the direction of the tangent at any point on a line of force would give the direction of the electric field at that point. Suppose we want to find electric field at this point somewhere here. Again, same thing we do. We draw tangent. Its direction would be like this. So this direction gives the direction of the electric field at that point. Do remember that the tangents only give the direction of the field, not the exact field only. So don't think the electric field is like this. It's only its tangent which is like this. So this would be the field direction. Fourth point is two lines of force do not cross each other. So if you assume that two lines of force cross each other, if for example think this as one field line, I'll call this as curve C1, and we'll take one more line of force which goes like this. We will call this as, say, curve C2. At the point of intersection, we will get two tangents, a tangent to the curve 1 and 2. If we draw tangent at this point, it will be like this. Think of tangent as, it will be like this, something of this kind. Think of a tangent only, it's like this. Similarly, if we look at curve C1 and if we draw tangent to curve C1, it will be like this. At this point it will be tangent here. So what we see is, we see that at the point of contact we are having two tangents. Now recall the previous slide discussion where we learnt that the direction of tangent gives the electric field at that point. Since in this case we have two tangents, this implies that at this point we have two electric fields. Now this is impossible because electric field at every point is unique and then well defined, which means at every point electric field value would be unique. It will have a given value in a given direction which is well defined. So we cannot have two possible fields here. Think of an example like this. Suppose imagine from some, say, tree. Think of this as Earth's surface, and think of a fruit. For example, think like a fruit, like an apple which falls from a tree. It is common sense that apple would fall towards the Earth's surface. That is because at every point the gravitational field is well defined. We know what the field value is and we also know what its strength is, direction also is. Imagine that at this point imagine that there are two field directions, which means there's one field like this, and also think of a case where we have one more field which is like this. So this would mean that at this point it would mean that this apple has two directions. So the apple can take either path 1 or path 2, but we know that at all the points the apple has a very defined path, which means having two values of the field is meaningless. So in the same way, even electric field also will have a unique value. So the assumption that both the field lines are present is not true, which means that two lines of force cannot cross each other. That's the fourth point. Fifth point is electric lines of force do not form any closed loops. Now a loop means, example, think that we start from say a point A and then we take some path to go to point B. So we start from point A and you go to point B like this. And if we come back from B to A in some other path or same path also, this is called as a loop. So loop would mean starting from one point and coming to the same point. In case of electric lines of force, we saw in the previous slide that we have a positive charge and a negative charge. We saw that the field lines start from positive and these field lines end at the negative charge. One field line was like this, one more was like this. Here the field lines always start from the positive charge and end at the negative charge. We don't find a case where a field line comes like this. This is not possible. So this means that electric lines of force do not form closed loop. We will learn later that magnetic lines of force forms closed loop but not electric lines of force. Now we will look at some configurations. In this case, if you assume that the charges as same magnitude also as given here, plus q and minus q, and if the distance between them is very small, then this configuration is called as a dipole. We will learn what dipole is in later topics. For now, think that a dipole contains two charges of same magnitude but different polarities, and also their separation is very small. So in that case, how will the lines of force be? To understand this, we will draw it separately. For a positive charge, the lines of force starts from the positive charge. It starts from positive charge and it ends at the negative charge. It goes like this. So you have a straight field line from plus to minus. If we add only a positive charge, then a field line was going like this. But because of the force of interaction, it's been modified now. So this minus charge will try to alter this, will try to pull it towards itself. So this field line will be pulled towards the negative charge. So it will go like this. And even here also, same thing happens. It's been pulled towards the negative charge. The charges, the fields which are close to the charges will be altered more. But something which is very far away, for example, this line of force is very far from the negative charge. So this is almost unaltered. Same here also, this charge, this line of force is very far from this charge, so it will be unaltered. But something which is closer, this is closer to the charge, so this also will be altered to some extent. So it will be bent and going like this. Same here also, it will bend and go like this. Now the charges, the fields far away, they are not altered so much. It will have small curvature. Same here also. So the basic point is, those lines of force which are close to the charges will be altered more than those which are far away. Example, this is not so much close, it will have a very small deviation, not much. It's almost straight line with a very small deviation. So same here also, these will have a small deviation and this will have small deviation. So this is the configuration of electric lines of force for a dipole. We can even draw the configurations for a system containing two positive charges or two negative charges. Now in this case, we'll take the first case where we have two positive charges. Now for a positive charge, the field lines would go outwards. What will happen is this field line which is trying to come will be pushed by this field line. So we won't have any field line which connects them directly. Now this field line is going like this. It's been pushed away by this field line. So it will be pushed away. It will be pushed away like this. Same here also, it will be pushed away like this. So close to the charge configuration, the field lines are pushed away by greater degree. Same here also, be pushed away like this. So even here same thing, been pushed away like this. So those field lines which are closer to the other charge would be pushed away to a greater extent. Now those field lines which are further away, this field line would be less affected or least affected. Same here also, this would be least affected. Something which is close by will be affected, but not to a greater extent. So these would be not much affected. So it will be just a small deviation as given here. There are small deviation here. So those field lines which are closer or like this or this will have more curvature. We can draw same thing even for two minus charges also. In this case, it is just that they'll have different or they'll have opposite directions. So compared with positive charges, for two negative charges, the field lines will have opposite direction as compared to the system of two positive charges. The next topic is called as electric flux. The symbol for this is called as phi, or some books write phi suffix e. This is called as phi, which is a Greek alphabet. Suffix here stands for electric field, because we will learn in later chapter about magnetic flux. So here this E stands for electric field. This whole symbol stands for electric flux. Now this is defined as the number of electric lines passing normally through any surface. So the number of electric lines passing normally through any surface is called electric flux. We will learn later that for it, the SI unit is Newton meter square per coulomb. So going forward, we will define a term called as area vector. So we'll define an area vector. Now until now what you have learnt is, you all might have learnt that area means only magnitude, but from now on we will treat area as a vector quantity. In fact, even a line, area or volumes, these can have direction themselves also. So don't think that line, area or volume only means magnitude. They can have some direction also. So in that sense, an area vector has both magnitude as well as direction. The magnitude would be the value of the area only. For example, if we look at a table like this, a table which has been drawn like this, if we assume that its length is say 2 meter for example, and its breadth is say 1 meter, in this case its magnitude of area would be length into breadth. So the value of A here would be 2 meter square. This is called as magnitude. This is what we're learning from high school or primary school. Now comes a very, very important idea, which is its direction. For an area vector or for any area, the direction is always normal to the surface. Normal here means perpendicular. So it is perpendicular to the surface, which means in this case, at any point, if you look at this point here or any point here, it's always normal. And normal here can mean two directions. Either it goes upwards like this is one direction, or it goes downwards also. So this is a direction. So it can't have two directions. It's any one of this only. Now it is based on diagram also. It is based on the problem also. So these are called as open surfaces. For open surfaces, it can have two possibilities. I'm not saying it has two area vectors. I'm saying it can have two possibilities. But for a closed figure, it has a very defined direction. It becomes clear in some few minutes. For now, remember that for open surfaces, the area can have two possible directions, upwards or downwards, while for closed surfaces, it is well defined direction. Now in this case, what I can do here is, if I draw a vector, okay, I can draw it anywhere. I can draw it here or here or here. These are called as area vector. So I'll put A with a arrow. These indicate area vector. Now in this case, these are parallel. So you can draw any one vector is sufficient. But if it's not parallel, it's something of this kind of a shape, So in this case, each point, you can assume that each point or each area into small areas. For example, look at a floor. If you look at a floor, it will have small amount of tiles in it. So you can think that the entire area is broken into small regions that I call as dA. So dA means it is a small region or small area. So each one is here a dA. Now each of this will have its own direction. For example, here it's normal to the surface. Here it's normal to the surface. Suppose somewhere here, if you take a small area somewhere here, for this small it will be normal to the surface. It will come out normally. So as seen in the previous case, if it's a flat surface, then for every small region, the region here or region here, at all the regions will have same direction. So if you look at each one as small area, it will have same direction. Unlike here, where in one case it's pointing like this, it's pointing here like this. So here they are different directions. So there's a possibility that for a given area, each small elemental areas can have same directions or different directions. Whenever the surface is flat, plane as given here, in that case, those small area vectors will be parallel to each other, while in some cases, the small area parts will not be parallel as given here. This is called as area vector. To continue forward, here I've taken few examples to demonstrate what is area vector is. In this case, if you look at this plane, so the direction would be coming towards us. For example, you can think of an arrow coming towards you. So the area vector for this plane is coming towards us. It's normal to the plane. We saw in the previous slide that area vector is always normal to the area. Now in this case, you can assume that we have three different areas. You can assume that it is one part of the area and this cylinders is another part of the area, or we can break this total area into three different parts. You can call this as area 1, this is area 2, this is area 3. We'll find out what is the area for each part. Now if you look at the first part of it, if we look at a small region here, a small area, For this small area, the vector would be outwards, normal to the small region. This is called as dA. While if you take another small part here, even for the small area, it will have same as this direction, it will be dA only. But if you look at small part somewhere here, like this, it will go out normal to that area. So you would find that for these small regions, they are same directions. But for the entire part, it's more like a cone. The entire conical part, it has different directions. Now observe one thing carefully here, that in all the cases, the direction is going outwards. So for a closed figure, for a closed object, for a closed body, it is always outward. Now to look at this point, if you look at the cylindrical part, then for a small region somewhere here, for a small part somewhere here, if you assume this area is dA, then for this, its direction would be going out like this. It will be like this, called as dA. For a part somewhere here, it will be going out like this. It's called as dA. You can do same thing on this side also, as well as for this part also. And coming to a sphere, look at the small part here, somewhere here. A small part, if you draw from the center, it would come out radially. It come out like this. So for this, it will be going out radially. So this would be its direction. If you look at a small part somewhere here, small part here, small area, then it goes out radially. So this is how its area vector would be. For the small part, it will be going out radially. Same for any part here. So for a sphere, area vector would always be along the direction of the radius vector. So you can draw same thing for these things also. For example, for the hemisphere, for the small part here, for small region, the dA would be from the center. It will be like this. This would be its dA. Now if you look at some other part here, even here also it will be from the center. Think from center, it will come out like this. This is what its dA would be. It will be normal to this part. So we see here that the directions are different for this region. So as I told you earlier, there can be cases where the area vector, the small area vectors could be parallel to themselves, or they could be in different direction also. So with this understanding, let's again define what is electric flux mathematically. So mathematically, it is defined as the product of area of the surface and the component of the electric field in the direction of normal to the surface. Now I'll repeat once more. It is the product of area of the surface and the component of electric field in the direction of normal to the surface. Now do remember two things here. If you have an area like this would be its plane, and something which is normal would be normal to the plane. So I call this as n cap. Now n cap means it is a unit vector which is normal to the plane. Basically n cap would mean direction of the area vector only. So what we'll do in this case is, we'll assume that we have a uniform electric field like this. The field is uniform. So let this be called as capital E. Suppose in this field, if you place a sheet of paper, something of this kind, such that the paper is normal to the field. It's normal to the field. So in that case, the flux is given as product of area of the surface and component of the field in the direction of normal to the surface. Just come back to in a minute. Think of a case where there is a small area is given here, a small area like this, and then the field is in this direction, while the normal to this area would be in this direction. We call it as n cap. N cap basically means here it is dA cap only, because dA vector, because it is a small region. Let the angle between the electric field and this direction be called as theta. So we have a component like this. This is what E is, and we can take two directions here. This would be theta. Now this component, if you call this as x and y axis, component of E along x would be E cos theta, and component of E along y would be E into sin theta. Now E cos theta is along the x direction. If you transpose this diagram here, it would mean that the component of E along n cap would be E cos theta. This would be E cos theta. The component in the plane of the area would be E into sin theta. But what we want is, by definition, we want the area vector, we want this dA, into the component of the field which is normal to the surface, which means it is E cos theta. So you want this dA into E cos theta. So if you rearrange this, write this as E into dA into cos theta, or it becomes E dot dA. So this is the flux through small region. It is E dot dA. Now suppose, imagine that we have a big object, something of this kind. We have an object like this, and this is part of the object. I want to find the flux of the entire object. So in that case, what we do is we divide this whole area into small regions, and then we find the flux for all small regions. I find the flux for this region, and this. So we find the flux for all the regions. But what I want is, I want the flux to the entire area. So the total flux to the entire region would be adding all the small fluxes. In this term, it is given as integrating all the small fluxes. Now in simple language, integration basically means adding or summation. The difference between sigma and this symbol is that sigma would mean adding for discrete variables, and some integration would be for continuous variables. This is what is called as phi. If we put it back here, then what we get is, it will be E into dA into cos theta. This is called as total flux. Now think of a case where theta is 0. If theta is 0, then what we get would be E into dA. Or we'll take a case where theta is constant, not 0. We'll take a simpler case. We'll take first case where theta is constant. In that case, even this term would be a constant. This comes out now. So phi is equal to E comes out, even cos theta comes out, into dA. E is taken outside because we assume it's an uniform electric field, which means field at all points is uniform. Now this means adding all the small areas. Then what we get would be total area. So therefore from here, the total flux is equal to E into A into cos theta, or it will be just E dot A. So the flux form could be just E dot A, or it could be E into dA into cos theta. And do remember that this form comes from here only. An example of this could be like this. Think of a case where you have uniform fields. Suppose if I place a plane which is like this. Then if you look at any small region here, for example, think of small region somewhere here, region somewhere here, region here, or something here. For this region, this is what dA would be. So angle here is say some theta. Even for this also, it will be same theta only, same theta here only. If you take any region here, take small region here, this is what angle theta would be same. Which means in this orientation, for all these small elements, the angle made with the field is same. So in such case, it becomes E dot A. So whenever the orientation is same, then it becomes E dot A. But if it's different, for example here, in this case area would be like this also, or something, maybe like this. There's different areas. So in this configuration, the total flux is given as integral of E into d into cos theta. So this is what is called as electric flux. Now dimensionally, the flux will take a simpler case where flux is equal to E into A into cos theta. Now dimensionally, this has no dimension, so it becomes meter square into dimension of E. So solve and see it. Put for E the dimension of E and solve and see it. You would get the dimension of electric flux. Next point here is electric flux is a scalar quantity. It is because you might learnt in vectors that A dot B would be A into B into cos theta, and this is called as dot product or scalar product. That is because the value what we get here is a scalar value. So hence this flux, which is dot product of E and dA, is a scalar quantity. Based on this, we have very important theorem called as Gauss Theorem. Now the question is, why do you want this theorem? Do understand that the aim of the chapter is to find the electric field, because for a given charge, electric field is the most basic and fundamental physical parameter. If we know what is electric field, then we can find what is electric force, we can find what is the potential energy as well as its potential. We'll see what these two terms are in the next chapter. But then for a given charge, electric field is the most basic physical entity. Now earlier we found out electric field using Coulomb's law, where we got E is equal to F by E. This is what was definition of electric field. But do remember that Coulomb's law is true only for point charges. Now think of a case where the body has something of this kind of orientation. Something of this orientation, where the charge is spread everywhere. If I want to find what is the field at this point P, then what I can do is we can divide this arrangement into small regions, and call the charge for any one as dq. For example, let this charge of the small region be dq. Then what I can do here is we can find what is the field because of this charge dq. It goes like this. The field goes out like this. In same way, we can find what is the electric field because of all such small arrangements and add them by using integration. Now this becomes a very challenging exercise because it is difficult to integrate such kind of configurations. It is not impossible, but it becomes difficult. So another way to find electric field is by using Gauss theorem. In fact, if we want to find electric field, We can do it in many ways. The first thing what we learned is by using Coulomb's law. The second method is what we'll learn now. It's called as Gauss Theorem or Gauss Law. In fact, there are many more methods also. There's something called as method of images, and there are many more methods also. There's something called as using Poisson's equation and all. But these methods are not for this course. It is beyond the scope of the syllabus. So what is in the syllabus is only the first two methods. We already studied the first method. Now we'll take up second method. But do remember that in all the methods, whether it is Coulomb's law or Gauss theorem or any other method, in all the cases we are trying to find the field only. So with this in mind, we'll define what is the Gauss theorem. Now it says that the total electric flux through a hypothetical, which means imaginary, closed surface is equal to 1 by epsilon naught times the total charge enclosed within the surface. To make sense out of it, think, for example, we have a charge, say charge Q1. Now, if I want to find the field somewhere here at the point P, then what I can do here is, if you want to use Gauss theorem, then we should draw a closed surface around this charge such that that closed surface passes to the point P also. So this surface which is drawn here, this is called as Gaussian surface. It's called as Gaussian surface. By this theorem, it says that the total flux through this closed surface is equal to 1 over epsilon times the total charge enclosed within the surface. So mathematically, this flux is given as Q enclosed. So here it stands for enclosed charge, enclosed by the Gaussian surface by epsilon naught. This is called as Gauss theorem. Now we should keep in mind that Gauss law can be used to derive Coulomb's law and vice versa. That is, we can go from here, we can arrive at Coulomb's law from here and then vice versa also. But again here, the scope of this derivation is beyond this syllabus scope. We will not do it, just understand the point here. Now, by convention, the flux into a surface is taken as negative and flux out of a surface is taken as positive. This is very important. So if you have, for example, some kind of a surface, if the flux is out of it, that is, if you have a case where the flux is outwards, it is taken as positive, which would imply that the surface is enclosing a positive charge. So in this case, the field lines will be going out like this. So the flux will be a positive. If the surface encloses a negative charge, something of this kind, minus charge here, then the field lines will be into the charge. In this case, the flux is taken as negative. Again, when is Gauss theorem useful? We'll see it in a minute. Gauss law is true for any closed surface, no matter what its shape or size is. That is, if you have a positive charge, for example, any configuration, I take a positive charge here, and then at this point P, suppose imagine, or this point A, we need to find the electric field. So for this, we use Gauss law. It doesn't matter what is the shape of the surface. You can take a surface of this configuration or this type. You can take something of this type. You can take any configuration. You can take something of this type. In all the cases, the flux remains the same. The flux through this surface or this surface or this remains the same. So the flux doesn't matter on what is the shape and size of the surface taken. Second point is, in the equation what we wrote earlier, that is flux is equal to Q by epsilon naught, we wrote as Q enclosed. Now here Q enclosed means it is the charge which is enclosed by the Gaussian surface. To understand this, imagine we have a charge. Say for example we have charge plus Q1. Somewhere here we have charge minus Q2, and somewhere here a charge plus Q3, a charge plus Q4, and a charge minus Q5. Suppose in this case, if we draw Gaussian surface, we draw a surface which is like this. Now this surface is containing only three charges, which is plus Q1, plus Q3, and minus Q5. So for this configuration, for this surface, Q enclosed here would be Q1 minus Q5 plus Q3. So the flux through the surface would be just these charges, that is Q1 plus Q3 minus Q5 by epsilon naught. So even though charges Q4 and minus Q2 are present very close to this configuration, but Q enclosed means only those charges which are present in the Gaussian surface. We'll take one more surface like this. We'll take this surface. For this Gaussian surface, the charge enclosed would be Q1 plus Q3 and plus Q4. If you look at a configuration which is like this, say you look at say like this. For this configuration, the charge enclosed would be Q3 minus Q2 and minus Q5. So the flux through this black surface would be Q3 minus Q2 minus Q5 by epsilon naught. So this is what is meant by Q enclosed. It is only those charges which are enclosed in a Gaussian surface. Now keep in mind that Gauss law is useful only if the system has some symmetry or some symmetry in the configuration. Now we can obtain this by taking a proper Gaussian surface. Now this point will become clear when we take some derivations. For now, understand the fact that Gauss law cannot be always used. It is useful only if you have some system in the configuration. We will take some numericals to learn the earlier concept. Example 1 says a charge of 8.854 coulomb is placed at the center of a hollow sphere of radius 1 meter. Calculate the electric flux emerging out. It is positive because we have a positive charge here. So question says calculate the flux emerging out of the sphere. Now we learned in the previous discussion that electric flux by Gauss Theorem or by Gauss Law is given as Q by epsilon naught. What is given here is, it says there is a charge of some value which is given as 8.85 coulomb. Now this charge is placed in a sphere. Imagine we have a sphere around this point. Just think we have a rough sphere here. Think of this configuration where charge is placed inside a sphere. This distance is given as 1 meter. The question says find the flux. Now we know flux is given by this formula, and from here Q is given as 8.854 and epsilon naught also is a constant value. That value is given as 8.854 into 10 power minus 12. Now from here this gets cancelled. So what we get from here would be flux is equal to just 10 power 12 Newton meter square per coulomb. This is what the flux is. Do remember here, it doesn't matter as to what is the shape of the object. So here the data of a radius of 1 meter doesn't matter at all. It's not required. Which means whether you have a sphere or something of this kind, or say a cone of this kind, whatever it's a configuration, through all this the flux would have been same only. Example 2 says a charge Q is placed at the center of a cube of side A. Find the electric flux through any one face of the cube. Now what is given here is a charge is placed at the center of a cube of side A. Now think of a cube. Like this. Now, at the center of this cube, a charge is placed, and the side of the cube is given as A. Question says find the flux through any one face. Now we know that a cube contains 6 faces. Think of your room. The room contains 6 surfaces. There will be 4 walls, 1 floor, and the roof. So the flux which comes out the entire cube would be Q by epsilon naught. But the question says find the electric flux through any one of the face, which means this total flux goes into all the 6 faces. So we can say that the flux through any one face would be 1/6 of it, because the cube contains 6 faces. So the flux through any one face, just call it flux through any one face, is equal to 1/6 of the total flux. That is equal to 1/6 into Q by epsilon naught. So this is a required answer. Thank you.